The universe, with its vast expanse and intricate workings, harbors many secrets. One of the most intriguing mysteries lies in the realm of negative matter. This enigmatic concept encompasses two distinct entities: antimatter, a mirror image of ordinary matter, and negative mass, a hypothetical form of matter with peculiar properties. While antimatter has been experimentally confirmed and holds a vital place in scientific understanding, negative mass remains a theoretical enigma, challenging the very foundations of physics. Antimatter, as its name suggests, is the antithesis of ordinary matter. For every particle of matter, there exists a corresponding antiparticle with the opposite charge. For instance, the negatively charged electron has a positively charged counterpart called the positron. When matter and antimatter collide, they annihilate each other, releasing a burst of energy. This process, known as annihilation, is one of the most efficient energy-releasing reactions known to science. In contrast to antimatter, negative mass is a hypothetical form of matter with a negative value for its mass. This seemingly paradoxical concept leads to bizarre predictions about its behavior. According to Newton's second law of motion, force equals mass times acceleration. If mass were negative, a force applied to an object with negative mass would cause it to accelerate in the opposite direction of the applied force. This counterintuitive behavior has profound implications for our understanding of gravity and the nature of space-time. The study of negative matter, encompassing both antimatter and negative mass, pushes the boundaries of our knowledge and challenges us to reconsider the fundamental laws of the universe. By delving into these exotic realms, we gain a deeper appreciation for the intricate workings of nature and the endless possibilities that lie beyond the familiar. Antimatter, a concept once relegated to the realm of science fiction, is a tangible reality. It is a form of matter that exists in parallel to our everyday world, composed of antiparticles that mirror the properties of ordinary particles. For every particle of matter, such as the electron, proton, and neutron, there exists a corresponding antiparticle with the opposite charge. The positron, the antiparticle of the electron, carries a positive charge, while the antiproton, the antiparticle of the proton, carries a negative charge. The existence of antimatter was first predicted by physicist Paul Dirac in 1928, who theorized that particles could have negative energy states. This groundbreaking idea led to the discovery of the positron in 1932 by Carl Anderson, confirming Dirac's predictions and revolutionizing our understanding of the universe. Since then, antimatter has been produced and studied in laboratories worldwide, providing valuable insights into the fundamental nature of matter and energy. Antimatter particles exhibit properties that are mirror images of their matter counterparts. They have the same mass and spin but opposite charges. For instance, an electron and a positron have the same mass but opposite charges. This symmetry between matter and antimatter is a fundamental principle of particle physics, reflecting the elegance and balance inherent in the laws of nature. The existence of antimatter is not merely a theoretical curiosity, but a testament to the deep symmetries that govern the universe. When matter and antimatter collide, they engage in a spectacular dance of destruction known as annihilation. This process, one of the most energetic reactions in the universe, converts the entire mass of the colliding particles into pure energy. The energy released during annihilation is staggering, dwarfing the energy output of even the most powerful nuclear weapons. This immense energy release stems from the conversion of mass into energy, as described by Einstein's famous equation E = mc2. The annihilation process unfolds with remarkable precision. When a particle of matter encounters its antimatter counterpart, their opposite charges attract each other, drawing them together in a fatal embrace. As they collide, their mass is instantly converted into energy, typically in the form of high-energy photons, also known as gamma rays. These gamma rays carry away the energy released during annihilation, leaving behind no trace of the original particles. The efficiency of annihilation is unparalleled. No other process known to science can convert mass into energy with such completeness. This remarkable efficiency has led to speculation about the potential applications of antimatter, particularly in the realm of energy production. However, harnessing the power of antimatter presents formidable challenges, as producing and storing antimatter in significant quantities remains a daunting task. Despite these challenges, the allure of antimatter's energy potential continues to inspire scientists and dreamers alike. In contrast to the tangible reality of antimatter, negative mass remains a theoretical enigma, a concept that challenges our intuitive understanding of the universe. Negative mass, as its name suggests, is a hypothetical form of matter with a negative value for its mass. This seemingly paradoxical notion leads to counterintuitive predictions about its behavior, defying the familiar laws of physics that govern our everyday world. The concept of negative mass arises from theoretical considerations in cosmology and astrophysics. It is often invoked in attempts to explain enigmatic phenomena such as dark energy, the mysterious force driving the accelerating expansion of the universe. Some physicists speculate that negative mass could play a role in the formation of wormholes, hypothetical tunnels through space-time that could connect distant regions of the universe. However, these ideas remain highly speculative, as there is no direct experimental evidence to support the existence of negative mass. The behavior of negative mass under the influence of forces is one of its most perplexing aspects. According to Newton's second law of motion, force equals mass times acceleration. If mass were negative, a force applied to an object with negative mass would cause it to accelerate in the opposite direction of the applied force. This counterintuitive behavior has profound implications for our understanding of gravity and the nature of space-time. For instance, an object with negative mass would be repelled by the gravitational pull of ordinary matter, creating a runaway effect that could have dramatic consequences for the structure of the universe. The interaction between negative mass and gravity is perhaps the most perplexing aspect of this enigmatic concept. Gravity, as we know it, is a force of attraction between objects with mass. The more massive an object, the stronger its gravitational pull. However, if negative mass were to exist, it would interact with gravity in a profoundly different way, defying our intuitive understanding of this fundamental force. The gravitational interaction between positive and negative mass is a subject of ongoing debate among physicists. Some theories suggest that negative mass would be repelled by the gravitational pull of positive mass, leading to a runaway effect where objects with negative mass would accelerate away from objects with positive mass. This counterintuitive behavior stems from the fact that a force applied to an object with negative mass would cause it to accelerate in the opposite direction of the applied force. In the case of gravity, this means that an object with negative mass would be pushed away from the source of the gravitational field, rather than being pulled towards it. Other theories propose that negative mass could create a gravitational field that is opposite in direction to the gravitational field of positive mass. In this scenario, objects with negative mass would still attract each other, but they would repel objects with positive mass. This unusual behavior could have profound implications for the structure of the universe, potentially leading to the formation of exotic objects such as wormholes and warp drives, concepts that have long captured the imagination of science fiction enthusiasts and theoretical physicists alike. The hypothetical existence of negative mass has sparked intriguing speculations about its potential implications for our understanding of the universe and the possibilities of interstellar travel. Among the most captivating ideas is the possibility of creating wormholes, hypothetical tunnels through space-time that could connect distant regions of the universe, allowing for faster-than-light travel. While wormholes remain purely theoretical, the concept has been explored extensively in science fiction and has captured the imagination of physicists and laypersons alike. The creation of wormholes would require the manipulation of space-time, a feat that lies beyond our current technological capabilities. However, some theoretical models suggest that negative mass could play a crucial role in warping space-time to create these hypothetical tunnels. By concentrating negative mass in specific configurations, it might be possible to distort space-time sufficiently to create a shortcut between two distant points in the universe. Such a shortcut would allow travelers to bypass the vast distances of interstellar space, potentially enabling journeys to distant stars and galaxies within a human lifetime. Another tantalizing possibility arising from the concept of negative mass is the creation of warp drives, hypothetical propulsion systems that could allow spacecraft to travel faster than light by warping the fabric of spacetime. Warp drives, like wormholes, remain purely theoretical, but the concept has been explored extensively in science fiction and has inspired serious scientific inquiry. Some theoretical models suggest that negative mass could be used to create a warp bubble around a spacecraft, effectively warping spacetime in front of the spacecraft and expanding it behind, allowing the spacecraft to surf on the distortions of spacetime and travel faster than light. The existence of antimatter has profound implications for our understanding of the early universe. According to the Big Bang theory, the universe began as a hot, dense state of pure energy. As the universe expanded and cooled, this energy condensed into matter and antimatter in equal amounts. However, the universe we observe today is overwhelmingly dominated by matter, with only trace amounts of antimatter detected in cosmic rays and high-energy physics experiments. This asymmetry between matter and antimatter, known as the baryon asymmetry problem, is one of the most fundamental mysteries in cosmology. The origin of the baryon asymmetry remains a subject of active research and debate among physicists. Some theories suggest that a slight imbalance between matter and antimatter arose in the early universe, perhaps due to subtle differences in the laws of physics governing these two forms of matter. This imbalance, however slight, would have led to the preferential annihilation of antimatter, leaving behind a surplus of matter to form the stars, galaxies, and planets we observe today. Other theories propose that antimatter may not have been completely annihilated in the early universe, but may instead be sequestered in remote regions of the cosmos, separated from matter by vast expanses of space. These hypothetical regions of antimatter, known as antimatter domains, would be effectively invisible to us, as any interaction between matter and antimatter would result in annihilation, producing a burst of energy that would be difficult to distinguish from other astrophysical phenomena. Despite its theoretical allure, negative mass remains an elusive quarry, a hypothetical form of matter that has yet to be directly observed. However, the quest for negative mass continues, driven by its potential to revolutionize our understanding of the universe and unlock new technological possibilities. Experimental physicists are exploring various approaches to search for evidence of negative mass, employing cutting-edge techniques and pushing the boundaries of scientific inquiry. One promising avenue of research involves the study of exotic materials with unusual electromagnetic properties. Some materials, known as metamaterials, can be engineered to exhibit negative refractive indices, meaning that light bends in the opposite direction when passing through them compared to ordinary materials. While negative refractive indices do not directly imply negative mass, they demonstrate the possibility of creating materials with properties that defy conventional expectations. Further research into metamaterials and other exotic materials could potentially reveal insights into the nature of negative mass and its interaction with electromagnetic fields. Another approach involves searching for signatures of negative mass in astronomical observations. Some physicists speculate that negative mass could be responsible for certain anomalous gravitational effects observed in galaxies and galaxy clusters. For instance, the observed rotation rates of some galaxies are higher than expected based on the visible matter they contain, suggesting the presence of an unseen gravitational influence, often attributed to dark matter. While dark matter is generally thought to be composed of weakly interacting massive particles, some physicists have proposed that negative mass could also contribute to these observed gravitational anomalies. The study of antimatter and negative mass is poised for a future brimming with possibilities. As our understanding of these enigmatic forms of matter deepens, we can anticipate groundbreaking discoveries that will reshape our understanding of the universe and pave the way for technological advancements that were once relegated to the realm of science fiction. In the realm of antimatter, researchers continue to refine techniques for producing, trapping, and manipulating antimatter particles. These advancements hold promise for developing more efficient methods of producing antimatter, potentially leading to its use in various applications, including medical imaging, cancer therapy, and even advanced propulsion systems. The development of antimatter-powered spacecraft, once a staple of science fiction, may one day become a reality, enabling humanity to venture beyond the confines of our solar system and explore the vast expanse of the Milky Way galaxy. The quest for negative mass is likely to intensify in the coming years as physicists develop new experimental techniques and explore theoretical models that could shed light on its properties and potential applications. The discovery of negative mass, if it were to occur, would be a monumental event in the history of science, revolutionizing our understanding of gravity, space-time, and the fundamental nature of the universe. It could also open up unprecedented technological possibilities, potentially enabling the creation of wormholes, warp drives, and other exotic technologies that could reshape the future of space exploration and human civilization. The exploration of antimatter and negative mass unveils a realm of profound mystery and boundless scientific inquiry. Antimatter, a mirror image of ordinary matter, has been experimentally confirmed and plays a crucial role in our understanding of the universe, while negative mass remains a theoretical enigma, challenging our intuitive grasp of physics and inspiring profound speculation about the nature of reality. The study of antimatter provides valuable insights into the fundamental symmetries and processes governing the universe. Its annihilation with matter releases immense energy, hinting at potential applications in energy production and advanced technologies. The mystery of the missing antimatter in the observable universe continues to puzzle cosmologists, prompting ongoing research into the intricacies of the early universe and the origins of matter. Negative mass, with its counterintuitive behavior and potential to reshape our understanding of gravity and space-time, remains a tantalizing frontier in theoretical physics. Its hypothetical existence could unlock extraordinary possibilities, such as the creation of wormholes and warp drives, concepts that have long captured the imagination of science fiction enthusiasts and theoretical physicists alike. As we delve deeper into the realms of antimatter and negative mass, we embark on a journey of discovery that promises to unravel profound mysteries and reshape our understanding of the universe. The pursuit of these enigmatic forms of matter is a testament to the enduring human spirit of exploration and our insatiable curiosity to comprehend the intricate workings of nature.